Do you believe in our founders' vision for America? That our republic will only survive if we are an educated and informed people who know our rights and duties. Since 1844, Hillsdale College has sought to educate all who wish to learn about these timeless principles of self-government. For more than 50 years, the college has worked to spread that mission by sending Imprimis to millions of Americans. Imprimis features some of the best speeches given at Hillsdale events, and now an audio version of the popular Speech Digest is available in a new podcast of the same name. And, like the print publication, Imprimis, the podcast, is always free. Listen to the best arguments from speakers such as Chris Rufo, Molly Hemingway, Mark Stein, and Hillsdale College President Larry Arnn, read by Hillsdale students. Subscribe today to listen to Imprimis at podcast.hillsdale.edu. That's podcast.hillsdale.edu or wherever you get your audio.
Welcome to the Hillsdale College K-12 Classical Education Podcast, bringing you insight into classical education and its unique emphasis on human virtue and moral character, responsible citizenship, content-rich curricula, and teacher-led classrooms. Now your host, Scot Bertram.
Thanks for listening. The Hillsdale College K-12 Classical Education Podcast is part of the Hillsdale College Podcast Network. More episodes at podcast.hillsdale.edu or wherever you find your audio. You also can find more information on topics and ideas discussed on this show at our website, k12.hillsdale.edu. We begin a series of episodes from presentations delivered at the Hoogland Center for Teacher Excellence seminar on the art of teaching mathematics. The Hoogland Center for Teacher Excellence is an outreach of the Hillsdale College K-12 Education Office, offering seminars in classical academics and pedagogy for teachers nationwide of any background. Seminars are led by the faculty, leadership, and master teachers of Hillsdale College. There is no cost to attend, and attendees may earn professional development credits. Currently, the Hoogland Center is hosting a series of events on the art of teaching. On April 11th and 12th in Ann Arbor, Michigan, it's the Art of Teaching American History. To learn more and to register, visit the webpage for the Hoogland Center at k12.hillsdale.edu, click the Events tab, and look for Hoogland Center for Teacher Excellence, or write to cte@hillsdale.edu. In November 2023, Dr. Thomas Treloar, professor of mathematics at Hillsdale College, spoke to a gathering of teachers and school leaders in an address titled, How to Think About Mathematics.
The title of my talk was given to me, How to Think About Mathematics, and don't presume that there's one way to think about mathematics. I'm going to tell you how I think about mathematics and maybe a good way to do so. I subtitled this Euclid and a Clear View of the Truth. Right? So there are K through 12, there's elementary school teachers, middle school, high school teachers here. And I decided to pick a topic, geometry, that I can sort of address this and give an idea of how would we, since I've been at Hillsdale College, develop this course, and why would we do it the way that we do it? How do we view the subject? So the first question I have for you is, why do we even study mathematics? I mean, why do we force kids, other than punish them, but why do we force kids to study mathematics? The art of explanation develops logic, building blocks of everything else. This is not an exhaustive list, but I think a lot of things were covered, right? To hone reasoning skills, right? To learn logic skills, to better understand the universe that we live in, right? Mathematics is a wonderful language for explaining many phenomena. Mathematical thought has influenced history throughout, right? And isn't it good to know how that occurred or where it touched the rest of the world? And honestly, sometimes we just study mathematics to study mathematics. I don't know about you, but I think it's fun. Right? It's interesting. It could be like a puzzle. And so, there's a number of reasons for studying mathematics. So what I want to do today is I want to talk a little bit about a course that we designed at Hillsdale College. It's one of our core courses. Students will either take this Math 105 course or they'll take calculus at Hillsdale. We don't offer anything other than that at the intro level. And I just want to talk a little bit about 105 and what we do and why we do it. And then I want to lead you through a good portion of this, right? So Math 105 begins with the study of logic. If we're going to hone logic and reasoning skills, shouldn't we spend a little bit of time studying logic? By the way, I have, at the end of this, I have various links, but the handouts that I actually, and many people in the department actually use for the logic portion of that class are at that link right there, and you could get access to them if you were so interested. But we start by studying logic, right? We continue by studying Euclid's elements, and we'll talk a little bit about Euclid's elements. Right? And then we finish with non-Euclidean geometry or other related type of topics. So why do we do that? Why do we pick geometry? Well, in K-12, or actually in K through 8, there's a good bit of study of quantity, right? Of number, of arithmetic, right? And most of arithmetic and algebra in that sort of K-8 is that study of quantity. It's a way to think about the world, the mathematical world, but it's not the only way to think about it. And so what is geometry? Geometry is the study of space. And geometry itself has its own sort of relationships in it. And I would just say that in any course, whatever you're teaching, you kind of have to know where your students came from and hopefully where they're going, right? Every course I teach, I want to have a narrative. Like we're building towards something, and we're building from what? Well, we started somewhere. All those students know something. What do they know, and where are they going to go to? And geometry is a great place because it's a little bit half step outside of that quantity study, of that arithmetic study. If students struggled with Algebra 2 in high school, I can still teach them geometry, right? At least the synthetic geometry that we end up teaching. So that is why we picked the course that we did. There's a lot of questions, why geometry, why Euclid? The other thing is, oftentimes in high schools, geometry is not taught in a synthetic nature. Right? It's what we'd call an analytic geometry. Geometry is a bunch of formulas, and we try to get the students to understand these formulas. Geometry at its heart wasn't that course, as we'll see in a little bit. So the other reason, there's one other reason why. I noticed outside, I didn't realize they were going to do this, but there are these videos out front. There say mathematics and logic on them. This was from an online course. So Hillsdale College puts together these sort of free, non-credit online courses. And a colleague of mine and I, David Murphy and I, we put together an overview of our Math 105 course, which is 10 lectures, all about 25 or 30 minutes long. And that's what's on this, along with about 20 minutes from Dr. Arnn, who's the president of the college. And so you can get a copy if you're interested. I'm gonna give even a quicker overview, but if you're interested in looking at more of this, this video that they have out in front actually covers it. And I don't know about you, but I'm assuming that there's a decent number of you that had to go online during COVID and maybe had to record yourself. I did, and it's not a lot of fun. I don't like to see myself, and I don't like to listen to myself speak. When you have professionals recording you, it makes a difference. I actually can listen to myself. I can actually watch myself. I think I'm kind of cool, well, they can make me look cool anyway. All right. So, couple of things. So we're going to go through this. I could have titled this synthetic geometry. I'm going to call it, I'm going to deal with Euclidean geometry. What is synthetic geometry? Synthetic geometry is just a geometry of proof. Synthetic geometry is when we start with axioms, we start with basic assumptions, okay? Self-evident assumptions, and we build up a body of knowledge. And so much of math is that, and yet we don't always teach it that way. I mean, we oftentimes teach mathematics as a bunch of things that must be memorized, and maybe over time students will piece those things together. And sometimes it's just worthwhile to see how this subject builds up. This is true with arithmetic, moving into algebra, moving into calculus later on, and it's certainly true with geometry. This is a nice reason to talk about geometry, is it's a little bit more self-contained. So Euclidean geometry comes from Euclid of Alexandria. Not much is known about him. He lived about 300 BC, 2,300 plus years ago, and he's most known for writing a book called The Elements. Now, what he wrote is not his own work, right? What he did, or at least not completely, there were a lot of things known. What he did is he organized things, right? He structured it and he synthesized it, and he started with what we would call 10 self-evident truths, first principles, right? 10 postulates, right? And from those, he used logic, and he produced or organized it as 465 propositions through 13 books. Which, keep in mind, because what we're going to do is we're going to do a quick overview of the first book of Euclid's Elements. And everything that we say is already true once we make our assumptions. We just don't know it yet. Right? And part of what we're doing through the first book, or all 13 books of Euclid's Elements, is just trying to understand what else is true that we just don't see yet. And we can go through that. It was the gold standard for geometry instruction for over 2,000 years, really 2,300 years until the end of the 19th century. It's the most popular textbook in the history of the world, and second most printed book in history behind the Bible. And when I went through graduate school and a postdoc and came to Hillsdale, I had never cracked open Euclid's Elements. Right? So, and it's where I studied a synthetic geometry in high school. It was a proof. We had our two-line proofs, right? We had two-column proofs. And it was a proof course, but it wasn't using Euclid. And it was a good course, and you can teach a good course in geometry without it. I'll just talk a little bit about Euclid. Because of those 10 starting assumptions, it makes it a good starting point for students. So, let me just lead you through Euclid's Elements a little bit, right? So any sort of synthetic geometry would start with definitions. It would start with postulates and common notions. So definitions, it's always good to take a look at this. I mean, we have to know what we're talking about if we're going to talk about them, right? I find in other disciplines, I love being in math because there's no arguing over what words mean, right? Everyone knows what a word means when we talk about it. But then we'll see definitions like this. A point is that which has no part. A line is a breadthless length. A straight line, number 4, a straight line is a line which lies evenly with all the points on itself. So what do those things mean? Like, what does it mean to think that a point is that which has no part? Well, we have this picture in our head because we're not just ignorant of what geometry is and what Euclidean geometry is, but we have this idea in our head, right? A point is that, right? Except for, given that definition, that's not really a point because that has a part. If that didn't have a width and a breadth to it, you wouldn't be able to see it. Okay? But just imagine that little point right there and shrinking it down and down and down and down, right? And somehow it's representing something inside of that, which is something that has no part. Right? So we have this model for what a point means. It's not in the definition, right, exactly, but we're trying to make sense out of it. So I want to talk a little bit about models with all of this. Okay, what's our model for a line? I mean, actually, a line itself is just one of those things, except, of course, that's not a line because it does have a breadth to it, or you wouldn't be able to see it. But imagine shrinking it down, right, not in that direction, but in this direction here, almost like a cut right there, right? And that's what Euclid means, or that's what's meant by a line. Okay? So a straight line is always an interesting one, and I'm going to ask for some feedback. Okay, a straight line is a line, so that's an example of a line. We'd call it a curve now, but a straight line is a line which lies evenly with all the points on itself. Well, what does that mean? It lies evenly with all the points on itself. Any ideas? No turns? I kind of think of it, it doesn't curve to the right or curve to the left. I definitely see this thing curving. That doesn't seem very even. I mean, we do have this picture in our mind of, well, I can't do it perfectly, but the idea of a straight line, that's usually what we call a line now anyway. A straight line, right? It doesn't turn to the right, it doesn't turn to the left. How else could we describe that? What's that? curvature, you get a curve. That's calculus, right? So we're getting into calculus. But yeah, it's not curving in either direction in perfect order, right? Which is very close to what that is. Sometimes we think about it as, sometimes people describe it as, it's the shortest distance between 2 points. Okay, right? So, I mean, we could model it by just, finding 2 points, and we could sort of pull a string as tight as we wanted to, and that's usually what we think. Because obviously, if we pull it tight, it's not curving to the right or the left. We're also putting a metric on it, right? We have to talk about distances, and Euclid didn't talk about distances in there, but certainly that's the way we could think about it. And early on, it would be the path that light followed was the idea, right? Right? That light, if it's, say, casting a shadow off of a building, the way that it casts a shadow would be that of, that's an awful picture, I know, but it'd be that of a straight line. Okay. But just think, we have this picture in our head because we have some experience, and we have a model. We have these things that seem pretty abstract, right? In fact, maybe incomprehensible, and we're putting some sort of physical meaning to it, right? Attaching some sort of physical meaning to it. And so one of the questions that I want you to think about is, does it have to be that model? What I laid out? Like, does it have to be? Because not only did I draw some pictures of what we call lines and points and straight lines, but I did it on this whiteboard here, which is flat, right? Does it have to be flat? I have a prop. Normally, I'd have a chalkboard globe, but they're more difficult to bring on the plane. So this is my $2 beach ball version of such a thing. But, we live on a big ball, right? It's not a perfectly smooth ball, but we live on a big ball, right? And could my geometry be on a ball? I use a small version of it, right? Because I could talk about lines, and especially if I'm going to talk about the shortest distance between 2 points, I could talk about points. I can put little dots on this ball just as easily as I can put dots on that board. And I can draw curves on this ball as easily as I can draw them on the board. And I could think about straight lines. I could take 2 points and I could pull a string tight between those 2 points. And when I pull a string tight between those, wouldn't that give me something that doesn't really curve to the right or to the left? So there's a question. Is this a valid model for what Euclid did in Euclidean geometry, or geometry in general? I've even drawn on this one already, and we'll talk about it a little later, a triangle, right? That started at the North Pole, came down to the equator, took a left-hand turn, went over a ways, and then took another left-hand turn and went back up to the equator. And all of those things are things I would call straight lines, right? And again, if I want to think about it, a good way to think about it is, pick 2 points and pull a string tight. So I'm going to come back to this. So I just want to talk, we have these definitions. Some of them are a little bit more comprehensible than others. So let's just keep going, right? The other definition I just want to make sure we have, because we're going to use it, is that of a circle. And a circle is, that's number 15 there, is a plane figure. So basically, a circle is a center, right? They have a center, and it's the collection of points that are all equidistant from that center. So if we needed to, right, we could have a compass, but I don't know if the sharp edge on a compass, if they'd let me bring that on the plane either. But, we can always take a piece of string and tap one side down and sort of draw a circle pretty easily. Right? We have those tools. By the way, I'm not going to pull the ball out at the moment, but we can do that on the ball also. Right? I can talk about circles on the ball. Okay? And it turns out the longitudinal lines on a globe, those are lines. The latitudinal lines, those are actually circles. Right? They're not actual lines. So, here we go. So then, once we have a collection of definitions, I think I have enough for now. Then we have some common notions. These are assumptions that Euclid said there's going to be 10 total assumptions. These things are true. What else is true in the world? So the things that are called common notions are very algebraic in nature, right? Things which are equal to the same thing are equal to one another. That's what we call the transitivity property. Okay? If equals be added to equals, the wholes are equal. If I have two things that are equal to each other and I add things to both of those that are equal to each other, the whole is going to be equal. Equals subtracted from equals, remainders are equal. Okay? Again, all of these are very algebraic. And all of these, if we're gonna rely on them to be assumptions, they're probably things that we're not going to argue about. It's like, okay, I can understand. Things which coincide with each other or one another are equal to each other. Right? So basically, if you can take two line segments, you can line them up perfectly. We're going to call them equal to each other. And then the last one is the whole is greater than the part. Yeah, you have something, you break it up into pieces. The pieces are going to be less than what the whole was, or the whole will be greater than those parts. Those are things we probably don't want to argue about, right? We can, right? And that's sort of, we're abstracting from the world how we know things sort of work, right? From the world, I know if I take something and break it up into pieces, if I'm going to mean anything by greater, the whole should be greater than the part, okay? Right? Then we get in, so those are very quantitative, those are sort of algebraic, and then we get into the postulates, and the postulates are the same, are similar assumptions, only they're geometric in nature, right? So these are the ones that actually seem like they involve geometry, right? And the first one is, I can draw a straight line from any point to any other point, right? So pick 2 points, I can draw a straight line. I tried to do that there, right? Pick 2 points, draw a straight line, right? Really simple. I can take a straight line and I can extend it as far as I want to, right? I can just extend it out farther. It seems reasonable enough. I can actually describe a circle once somebody gives me a center and a distance. All right angles are equal to each other. Well, we'd have to think about what the definition of a right angle is. And I'll just say the definition of a right angle is if I have a line here, right? And I have a line here, and I set a line on top of another line, and these two angles are equal to each other, then I call it a right angle. And so what Euclid is saying is all of the right angles are equal to each other. It's always it's an interesting thing. I won't do it right now. If someone wants to ask a question in Q&A at the end, how could right angles not be equal to each other? It's possible, right? We could come up with a model where that's true, where right angles there are different types of right angles. But that's not what Euclid's assuming. It's not going to happen on the ball. All right angles are equal to each other on the ball, and all right angles are equal to each other on this board. So, with those 4 postulates and the common notions, we would be in this world called neutral geometry. Okay? Actually, it wouldn't be called Euclidean geometry today, right? Neutral geometry. Without a statement about parallel lines, some assumptions about parallel lines, we're in this world called neutral geometry. And so if I were just to assume those 4 postulates along with the common notions, I could prove a lot of things, right? And I would be proving things in the world of neutral geometry. But then if I assume also that 5th postulate, and if you notice, that's a longer, and it looks a little bit more complicated, if a straight line falling on 2 straight lines make interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on the side in which the angles are less than 2 right angles. That's actually a statement about parallel lines, and that, in fact, when we don't have parallel lines. And that's a much more complicated statement than I can draw a straight line between 2 points, or all right angles are equal to each other. And there's a reason, because this idea of parallel lines is a little bit more complicated than some of these other things. All right. So, but once we make an assumption like that, or a similar assumption, we're in Euclidean geometry. And given those 10 assumptions, right, those 10 statements, there's a bunch of things that are true. There's 465 other statements, at least in Euclid's books, that are also true. And so let's just look at some of that, right? So what I like about synthetic geometry is this is a situation that students can get their hands dirty, right? They can actually play with things and try to understand how these things fit together. Constructions are a big part, and is a great part. Right? The first proposition is what I'd call a construction proposition, right? It is if you give me a straight line, I can construct an equilateral triangle on it. And an equilateral triangle is a triangle where all the sides are equal to each other. Here's a book. There's a lot of different versions of Euclid's Elements. This is a copy from Burns' Euclid. I use that. It's pretty, right? It looks nice. And I found out a couple of weeks ago. I didn't fact check this, so I think it. I don't know why it wouldn't be true. Burns actually, I guess, a printing house went bankrupt because from printing this version because of all the colors that he used. Right? 4 colors in there. You didn't do that. You didn't do that back in the 1850s. Right? But how do I construct an equilateral triangle? Well, so I'm on a line segment. Well, that black line there is my straight line. Okay? So I'm just going to draw 2 circles. I'm going to, you might know this. I mean, you probably already know this. But on the left-hand side, I can take the left-hand side of that line segment to be the center, and then the radius, right? The distance would be the length, and I could draw that blue circle, and then I could do the same thing where I could let the right-hand side of that line segment be the center, and I could take the radius to be the line segment. So I get these 2 circles, and now I'm going to look at this point where the blue and the red circle overlap to each other, right? And I'm going to pick a point there. And now that I have a point there, I'm going to draw a straight line, right, back to each edge of the line segment. I could do that by postulate 1. So I can draw circles because of postulate 3, and then I can connect those line segments by postulate 1. And then I know that the yellow line segment's equal to the black line segment, right, because they're both the radius of a circle, and that's the definition of a radius. I know the red one is equal to the black one. Why? Because they're both radius of a circle. Okay? I know the yellow one is equal to the red one. Why? Because of the transitivity common notion 1, right? So now I have this triangle where all the sides are straight lines and they're equal to each other. It's not a difference. It's the first one, right? But I just draw a couple of circles. I actually construct it, and there you go. All right. So with those initial 10 assumptions, I didn't realize that I could draw an equilateral triangle until I did it. And now I know, you know what? I can draw equilateral triangles. Another thing Euclid did not assume was that you could move things around the plane, right? So here's a statement, right? To place at any given point as an extremity, a straight line equal to a given straight line. Well, what does that mean? Right? So I have this point and I have this line segment. I'm going to call my line segment BC. I'm going to call my point A. Basically, Euclid is saying, you know what, I can take that line segment BC and I can move it around the plane. I can move it to wherever I want to. I can move it over to the point A. There's nothing under the assumptions that says we can move line segments around, and yet it turns out it's true. Okay, how can we show it's true? We'll just go through an argument. I have my line segment BC, I have my point A. I'm going to draw a line between A and BC. Students can learn this, right? They can learn this process, and it helps them remember how to go through this, right? They draw a line segment. Once I have a line segment, I can construct an equilateral triangle on top of it, right? By drawing those 2 circles and getting that equilateral triangle. That's proposition 1. And then I could take that equilateral triangle and I could extend those lines out as far as I want to. So DB, I'm going to extend that one out. DA, I'm going to extend that one out as far as I want to. That's what postulate 2 says I could do. And then I'm going to draw a circle. Basically, I'm doing a bunch of pivots, right? I'm going to draw a circle that's centered at B and has length BC, a radius BC. And then that gives me this little point G down in the corner where it intersects. And I know something now. I know that BC is the same length as BG because they're both the radius of a circle. And we can systematically go through this. Now I'm going to get rid of that, and now I'm going to draw a circle at D that has length DG. What's that going to do? That's going to give me this point down here, call it point L, right? And now I have something, right? Now I have something that can actually compare. My claim is that AL is equal to BC, right? It's at the right location and it has the right length. How can I tell it has the right length? Well, DL has the same length as DG because they're both the radius of a circle. But remember, DA and DB are both sides of an equilateral triangle, so those things are equal to each other. And what happens when you take equals away from equals? The remainders are equal, right? So that's our common notion 3. So that right there tells me AL and BG are equal to each other. And then I can go ahead and say, well, I already knew BG and BC were equal to each other. Oh, so I'm done because AL and BC are equal to each other because equals, 2 things equal to the same thing, the transitivity property, are equal to each other. Right? I always like to put at the end of it, the entire construction, right? That's all the circles. I erased them as we went because it's kind of nice to see the cleaner but once we construct that, we just now have to go through and make the argument for why the thing that we drew, we believe it's the same or why it must be the same as before. And one other thing with Euclid, you can notice that he uses QEF. You might have heard the term QED, quod erat demonstratum, quod erat faciendum. QEF is used at the end of constructions, and QED, quod erat demonstratum, is used at the end of everything else. So we have done what we said we're going to do, where we have constructed what we said we were going to construct. And this is sort of a great subject. Notice I'm not assuming that I have a ruler and I can measure lengths, and I'm going to measure a length and I'm going to take it and I'm going to move it over to somewhere else. Right? That would be putting a measure on it. That'd be getting into a different type of geometry. Okay? This would be synthetic geometry, where we're just allowed to work with our straight edge without ruler lines on it, with our compass, right, to draw circles. The other thing about compass, when I pick up a compass, if there's nowhere is it assumed that I can pick up that compass and move it somewhere else. That in some ways, when I pick up my compass, the compass will always snap shut, I have to assume. Well, Proposition 2 allows me to pick up my compass and keep it, I keep that distance in there, because it allows me to move distances over distances. You can ask, can we do this on a ball? You could play with it. Seems like we could. It seems like we shouldn't have any problem drawing an equilateral triangle, and it doesn't seem like we should have any problem under these assumptions moving line segments. I'm going to be a little cryptic on that, but it seems like that. And then you go on, and I'm just gonna give highlights here, but we have congruence theorems, right? So now we have something that allows us to compare lengths at a distance. Okay? That wasn't part of the original assumption. And then we start getting into triangles, and we can compare triangles at a distance. Okay? There are these congruence propositions at side angle side, side side side, which basically say if I have two triangles and I have two sides, and the angle that's between those two sides on one triangle equal to the corresponding things on the other triangle, then the triangles are congruent, right? And what that means is all of the sides are equal, all of the angles are equal. And in fact, even more than that, the areas are equal to each other, okay? Right? So everything about those triangles are equal to each other, just moved at a distance. Okay? So the first one would be the side, side, side. The second one would be, side angle side. The second one would, in Proposition 8, would be the side, side, side. And then once we're armed with these things, okay, and you can see I'm skipping over things a little bit, right, to kind of move through this. But once we have these, we can start doing other things with our geometry. Again, they're not things that I necessarily assume are true. They're things that I can show are true once we started with those original Penn propositions. And so the next set, and I think construction has a wonderful place in a geometry class. Straight edges and rulers. Students can actually play with these things and try to understand them. Right? Proposition 9 is bisect an angle. I still remember in high school, many years ago, that when we bisected an angle, I remember my teacher telling me, you know what, but you can't trisect an angle. And I said, oh, I bet you I can. And I went home for 2 nights and I tried to trisect an angle. No, you can't trisect an angle. It's not possible. But I think I don't remember exactly. I'm sure I learned some things by trying to do it. I should have known then I was going to go on to life and math. I didn't think I was at that time, right? Right? And bisecting an angle is so simple, right? And given what we had, right? We never assumed that we could break an angle into 2 equal angles, right? But there's a really quick argument, right? There's my angle. I'm gonna bisect the angle at A, right? So what am I gonna do? I'm gonna draw a circle at A, right? And then that gives me this point at D, right? D that intersects on one side, and E that intersects on the other side. And because they're both the radius of a circle, those two things are equal to each other. Right? All right, get rid of that circle. I'm gonna draw a line segment now between D and E. And if I have a line segment, what can I do now? I can draw an equilateral triangle on top of it, right? I can draw those other 2 circles, and I could draw that equilateral triangle. And in particular, I have my point F. FD is equal to FE, right? So now I can see I have these 2 line segments on one side equal to the 2 line segments that correspond on the other side. And now let me get rid of those, and let me put a line segment from AF. Right? And now I have 2 triangles, one on the top and one on the bottom. in which two sides and two sides. So I either need to show that there's some angle equal to each other or a third side. But of course, AF, right, is on both triangles. And of course, AF on the one triangle coincides with AF on the other triangle. That's what we mean by things which coincide or equal to each other. So those things are equal to each other also. And now I have these two triangles that satisfy this side-side-side congruence theorem. And therefore it means that, well, that's all the sides, but the angles are all equal to each other. Right? And in particular, those angles at A are equal to each other, and that's what it means to bisect an angle, is to construct a line segment coming out of that angle in which those two sides are equal to each other. So this is where, as a teacher, and you should have your students think about, could you do this with a ball? Okay. And there's really nothing that should have happened here that would tell me I couldn't do this. In fact, I can bisect angles all day on a ball. Okay? So this is my model. For the most part, this seems okay. Right? And so why don't we think about Euclidean geometry? We always think of Euclidean geometry as being flat. Right? Why isn't it on the ball? Because we're not done. Right? In fact, we're overlooking some things, and we'll have to see soon. Okay? So I'll just point out, we keep going with this, right? There's the complete construction. It's always nice to see the complete, right? Once you know to construct these things, and there's a systematic ordering to doing so and to sort of making sense out of it, right in that picture is everything that we would need to know. We just then have to, use our different propositions to show that the appropriate things are equal to, or the common notions or the postulates are equal to each other. Okay? I want to point out that throughout this, and so this would get us up through proposition 12 of the first book of Euclid. We've only used three postulates. We've only used basically that we can draw straight lines between points, that we can extend lines, and that we can draw circles. Okay? We haven't said anything about right angles, and we haven't said anything about parallel lines. We actually sort of break open right angles in proposition 14 and 15. Okay? But I want to talk about proposition 16 because it is a big one. And when you're going through something, there are important things and there are not so important things. I say to my students, I'm teaching a probability class that uses the calculus sequence as a prerequisite, and I tell them, maybe about a third of what you learned in multivariable calculus is actually important. And their jaws drop. It's like, there are some things more important than others. Their jaws drop, right? They think if we say it, it's all important all the time. But that's not true, right? Some things are more important than others. Some things advance what we're trying to do more than other things advance them, right? I think that's part of the authoritative pedagogy, right? Where somehow everything that ever comes out of our mouth, we just throw it out there and they think of it as important. There are important conversations to have. There's important things to point out. And then there are things that really do advance what we're trying to do. And it turns out proposition 16 is one of those things that's really important in terms of understanding how geometry works, especially in Euclid's first book. Right? And here's what it says, right? It's oftentimes now called the exterior angle theorem. And it says, okay, if I have a triangle, and if I extend one of the sides of the triangle out, then what I get is what's called an exterior angle on the outside of the triangle. Right? And what this says is the two interior angles on the opposite side are less than the exterior angle. Exterior angle is greater than either of those two interior and opposite angles. Okay, so just really quick, a lot of propositions, there's a construction and then you show it's true. Right? So I have this triangle. I'm going to bisect one of the sides. And then I'm going to draw a line and I'm going to extend it as far as I can. I can do that by the postulates. At this point, we're getting good at this, right? Then I'm going to draw a circle and I'm going to make sure that I have these two sides that are equal to each other. And now I'm going to draw a triangle there. Okay? And I have these two triangles in which I can see on one side, two sides are equal to two corresponding sides there. So if I can show those vertical angles are equal to each other, right in the middle there, then I'm done. I have the side-side-side congruence postulate, but of course I do. That was a proposition before this, right? Those two angles, when I have lines crossing with lines, I'm holding on to this still. When I have lines crossing with lines, right, they produce lines, these vertical angles are these angles that are equal to each other. It's one of the first propositions that talks about right angles, it turns out. And so now I have these two triangles that are congruent to each other. And in particular, those two angles are equal to each other because they're congruent. And notice what we have here. This angle at the top is equal to this other angle. But the angle there at the bottom is less than, it's only part of that whole exterior angle, right? And the whole is greater than the part. So the whole is greater than that part, and that part is equal to that other angle, and therefore that whole exterior angle is greater than that top angle. It seems pretty anticlimactic. Why is that one so important? Because that one I can show doesn't work on here pretty easily, right? That somehow we made an assumption somewhere that this would fail. And in fact, this triangle right here does that, right? What's wrong with this triangle? Right, it doesn't count for the curvature. But how does this triangle that I have drawn here violate the exterior angle theorem? Yeah, the exterior angle here is 90 degrees, right? Whenever I take this right turn, and there's two things. Now notice something else. There are two right angles here. What's true about triangles? The angle sum is 180 degrees, two right angles. So obviously there's something going wrong here, right? But even at this point, I haven't assumed anything about parallel lines, but there's an exterior angle here that's equal to that exterior angle, and that can happen. And in fact, I could have gone farther. I could widen this triangle out pretty much as far as I wanted to, and I could make this top angle as big as at least up to about 180 degrees. So I could have done that, and I could have actually made the top angle, if I wanted to, greater than that one over there. So there's something about the ball that, and we haven't used the fifth postulate, that doesn't satisfy the first four postulates. But it's good to think about it. We can come back to it at the end, but what is it about the ball that doesn't satisfy those first four postulates? So, we move forward, right? In proposition 17, sort of as the next one, basically says if I take two angles together with any two angles, the sum is going to be less than two right angles, but we know if we add all three of them together, we should get two right angles, right? So we can keep going, right? That's certainly, though, not true until the parallel postulate. Proposition 18 through 20, I mean, we have a bunch of propositions along the way. You know, it's good to go through them. It's good to understand how geometry fits together. But I want to go straight to proposition 27 because it's the first statement about parallel lines. It says, if I have a straight line that's falling on two straight lines and they make alternate interior angles equal to one another, the straight lines are parallel to one another. Basically, that picture, I have those two straight lines and I have this transversal, and if the alternate interior angles, that angle there, right? That angle there, and oops, I'm really shaky, that angle down there, right? If those are equal to each other, it says we absolutely have parallel lines. Well, why? Well, this is an area, and this is why it's great to talk about logic. There's a type of mathematical logic which is called reductio ad absurdum, proof by contradiction, right? And how could this be false, right? That I have this angle relation about the alternate interior angles, yet the lines makes the lines parallel. The way I could make that false is by having angle relations and the lines not be parallel, right? So if I could find a situation where I have that angle relation and the lines aren't parallel, then this would be a false statement. Or if I could show that's ridiculous, that's not possible, then I could show that this statement is true. And so that's what you do, right? So you say, okay, I'm going to assume I have these angle relations, and I'm going to assume that those lines aren't parallel. Well, what does it mean for them to not be parallel? It means they're going to cross somewhere. Okay, this is actually a triangle right here. They're going to cross somewhere. But notice, if they cross, I am violating the exterior angle theorem, right? That this angle here, this is an exterior angle for that triangle, and this angle here is actually equal to that one. And I know that's not possible. So if it's not possible, that's ridiculous. If that's ridiculous, then my assumption that those lines could be parallel is ridiculous, and therefore those lines must not be parallel. Right? We can work our way up here. By the way, we still haven't used the fifth postulate. We still have not made any assumptions about what it means to be a parallel line other than parallel lines, lines that aren't parallel will cross them. And so we are still in neutral geometry until proposition 29, which is the converse of that statement, right? The 27 is if we have these angle relations, then the lines are parallel. And 29 is if the lines are parallel, we have this angle relation. And it turns out that statement there is just equivalent to the fifth parallel postulate. It's basically a restatement of the parallel. And so once we hit 29, we now have Euclidean geometry. We're outside of neutral geometry, and we absolutely know we're on this board. We knew the whole time once we got to 16 we weren't on the ball. But there are other models. There are other things that you could do. So once we have the parallel postulate, that's when sort of what we oftentimes remember in geometry is going to be true. There's a transitivity of parallel lines. If lines are parallel to the same line, they're parallel to each other. Angle sums are equal to two right angles. That's only a statement that's true once we assume the parallel postulate. It is possible for angle sums to be less than two right angles, but not once we assume the parallel postulate. And then going through, this is right at the end here, going through the Pythagorean theorem at the end, right? The book one, there we go. Book one ends with the Pythagorean theorem. Most popular theorem, mathematical theorem in the history of the world. Students know a squared plus b squared equals c, right? They know it. They don't always remember why, but they know that, right? And it's a good picture. Again, from Byrne's geometry, Euclid did not think as quantity, right? Wasn't thinking numbers, right? It actually was, I can produce, if I have a right triangle, I can produce squares. I can actually build squares on the sides of those at the triangle, and the sum of those areas of the two sides is equal to the sum of the area of the hypotenuse. The very area-driven type of argument. And in our 105 class, that's where we try to get, right? It's good for students who know the Pythagorean theorem is huge, right? Any distance formula that we would have at any point through algebra and the rest of it is driven by the Pythagorean theorem. And it's good for students to understand that they could start from basically scratch and they can prove this, not in 45 minutes. We don't have enough time in 45 minutes, but over the course of about 8 weeks, which is what we end up doing, right? And so, I mean, what do we do in this course, and what do we do? Right? We start with some basic. The students come in with some sort of knowledge, and what we're trying to do is build on top of that knowledge. We use logic and reasoning to determine other true statements, right? Models are huge, right? Because even in arithmetic, that's true, right? 3 plus 7 equals 10, right? Does it matter if it's 3 carrots or 3 cars, or 3 whatever? No, it doesn't. Does it matter if I start grouping things together rather than by 10s, by 5s or 8s? More or less, no, right? I mean, I'll get different number representations, but it's still the idea, Dr. Gregg said last night, of 51ness. There's something about 51ness. Whether I bunch things in 7s or in 10s, that still makes it a 51ness, right? We can determine new statements and we can test consistencies. And that's one thing that I think is really important in this day and age. When we have inconsistent thoughts, when we don't have things that fit together, how does it, how can we understand, can we recognize that's going to happen? So, resources, I just want to point, there's a website where you can actually watch the online course, although I didn't realize that they're giving copies out, so that's the same thing that we have there. Several different versions of Euclid's elements up there. If you're interested, the Poincare disk model, right, is a non-Euclidean geometry, so it would satisfy the first 4 postulates, unlike the spherical, but it's a different type of picture. And if you're interested in logic handouts, and logic is a lot of fun to cover with students because they oftentimes don't have a formal study of logic in K-12. It's a great thing. So anyway, I better stop there.
That was Dr. Thomas Treloar, professor of mathematics at Hillsdale College, and his lecture, How to Think About Mathematics, from November 2023. To learn more about the Hoogland Center for Teacher Excellence and to register for upcoming events, visit the website at k12.hillsdale.edu, click the Events tab, and look for Hoogland Center for Teacher Excellence. Or write to cte@hillsdale.edu. I'm Scot Bertram. We invite you to like us on Facebook. Search for Hillsdale College K-12 Classical Education. You also can follow us on Instagram at Hillsdale_K12. Hillsdale_K12 on Instagram. Thank you for listening to the Hillsdale College K-12 Classical Education Podcast, part of the Hillsdale College Podcast Network. More episodes at podcast.hillsdale.edu or wherever you find your audio.